Guys for today. So how many of you guys were able to finish it?
Yeah.
Alright, a good number. So if you haven't, pay attention. You'll be able to do this stuff no problem. So the problem, we have 4 binary mixtures, A, B, C, D. You don't know which compounds, so our goal is to find which are the components in this mixture, and also to match the pressure, temperature, and XY diagrams. So let's start with the TXY and the temperature and the pressure diagrams. So first thing, to make it easier, we have 4 binary mixtures, and by inspection you can tell 2 of the mixtures have azeotropes. So Professor Duncan touched upon that before we got going. As you can see, when the X and the Y are equal, there's an azeotrope. So we'll split them up, and it'll be easier to inspect which pressure diagram goes to which temperature diagram. So regardless if it's temperature or pressure, the azeotrope is going to occur at the same composition. So as you can see here, plot 1 for the temperature corresponds to plot 4 for the pressure. That's because the azeotrope is occurring at the same composition. So that's right away, you're like, those are the same, and then these plots are the same binary mixture. Now what do we do for plots 1 and 4 and 3 and 2? How do we see which is which? First thing you can check, a lot just happened right there. First thing you can check is what are the conditions for this temperature plot. For example, this temperature plot occurs at 1 atmosphere, and you know the liquid and the vapor are 100% composition at 102 degrees Celsius. So you can look at your pressure plot and see which plot corresponds with the information given here. As you can see here, that white star, the white star up top, this pressure plot is given at a constant temperature of 102 degrees Celsius. And there's X and Y are 1 at 102 at 1 atmosphere. And this plot's at 1 atmosphere. And at 102 degrees Celsius, the composition for the liquid and the vapor is 100% substance 1. Is that clear? That's one dead, right away you can tell which plot is which. And also you can kind of compare the distances between the liquid and the vapor, the timelines. So at a constant temperature here, the width should be similar to a point on the pressure plot. So that's an easy way to tell. The liquid vapor timelines are much wider here, so 2 must go with 3. Here, 4 must go with 1. So again, we're filling up the information. Next, let's just break down a temperature XY plot. Let's just get our bearings. I know we're looking at pressure, temperature, and also XY diagrams. It can get a little confusing in what's what. So first off, define where are the liquid vapor regions. At the lower temperature, you're going to have a liquid. As you increase temperature, liquids start to boil. So that's kind of intuitive that your liquid region is going to be at the bottom on a temperature plot, and your vapor is going to be on the top, and then LV is the land in between. Then you know your liquid equilibrium line is here, your vapor equilibrium lines up top. We have constant temperature, so I know you guys were doing flash room problems, for example. If you had a flash room at 190, it would separate into vapor and liquid. And then also you have your constant composition line. And then we have some more information that we can extract from this plot. So the azeotrope occurs at around 0.25% substance 1 in the liquid and the vapor. So to the left of the azeotrope, if you were to draw a tie line, you can see that the liquid has a greater composition of X than the vapor. Is that everyone? So left of the azeotrope, the composition of 1 is less in the vapor than it is in the liquid. So that means substance 2 is more volatile. So what does it mean to be more volatile? A substance with a lower boiling point is going to be more volatile because it can go into a vapor easier. So if you know, even though to the left of the azeotrope, if X has a greater composition of the liquid, but less in the Y, in the vapor phase, you know that the second substance is more volatile. It's more likely to go into a vapor. But then to the right of the azeotrope, the opposite is true. Substance 1 is more volatile. Because the composition of the liquid is less substance 1 and greater substance 1 in the vapor phase. So that's kind of breaking down the temperature diagram. Now let's break down the XY plot that we're looking at. So first thing, we have a constant composition, x equals y here. And then again, we're back to that x is less than y information. So how do you know it's x is less than y? To the left of the azeotrope here? Well, you can look at, let's say, 40% composition. We have 40% on the equilibrium line. Let's go to an example. To the left of the azeotrope, we have around 68% liquid and around 79% vapor. So we know that the vapor is greater, the substance 1 composition is greater in the vapor phase than the liquid phase. So there's a lot of information that you can kind of extract from these x, y, and temperature plots. All right, so now we're going to compare the temperature to the x, y. Does anyone have any ideas how you can do that? Yeah, Leah? Yes, so the first thing we can do is, again, we can match the azeotropes. So the azeotropes are going to occur at the same composition for the liquid and the vapor. So again, we have plot 1 for xy is occurring around 80%. So then we can look at the temperature plot. The azeotrope occurs at around 80% composition of substance 1 in the liquid and the vapor. So that's one key giveaway of which plot is which, is again looking at the azeotropes. But for the plots that don't have the azeotropes, what can we do? We can look at to see if the x's, if substance 1 is more volatile or substance 2 is more volatile, or even easier, you can read and match the equilibrium points. So I know a few of your exercises you were given the temperature xy plot and you had to create the xy diagram. So for example, here, if you were to draw a timeline at 110 degrees Celsius, you know the vapor is 0.6 and the liquid's around 0.45. That should correspond on a point on the xy diagram. So we'd look for 0.4 on the liquid and around 0.45. So then the xy, again, we filled in the binary information for the xy diagram with the temperature plots. And now probably the easiest part is determining the components for the binary mixture. And how do you do that? Just look at the boiling points on the temperature xy plots. So what's the boiling point? Can you guys tell me what the boiling points of the two mixtures are? Pure species.
Oh.
Yeah, Nick?
It's about 184, 185, and then looks like 148.
Perfect. So pretty close. So really you would just look at when it's pure species 2, we have a boiling point of 182. When you have a pure species 1, when it's 1 composition, the boiling point is 145 degrees Celsius. So who can tell me which species is more volatile?
Species 1.
Species 1? Why?
Because it has a lower boiling point.
Yep, perfect. So substance 2 has a greater boiling point. So 2 is said to be less volatile than 1, whereas Joel said 1 is more volatile than 2. But now a special note, if you look at the azeotrope, what's the boiling point of the azeotrope?
Higher than the boiling point of either of the species.
Yeah, it's higher than both the species, pure species. It's around 200 degrees Celsius. So therefore the azeotrope is less volatile than both pure species independently. Or both pure species are more volatile than the azeotrope in this case. So that's how you identify which components are in each binary mixture, just looking at the boiling points of the pure species. So that's probably the easiest part of the exercise. And so I won't go through each of the binary mixtures, because you guys can do that on your own. But the solutions are here, and they're posted online. So the corresponding information is for the pressure plot 4, the temperature plot is 1, the xy is 4, and the components are phenol and method period. Any questions? The solutions are posted online. You guys can check them out later. All right.